We're going to take a look at our exponential equations and graphs review for a test. I'm going to have some videos posted on how we will do some of the calculator stuff. You'll hear me refer to a calculator, but I have these already pre-done, so we'll just refer to the answers. If you have a question on how the calculator is to be answered, you can click on a video. I'll try to put it in the home screen. All right, first of all, we've got to refer to our formulas. We're either going to use the continuous compounding that involves the e, or we're just going to use one of our compounding interests. Just keep an eye open for that word, continuous. So it says a deposit of $270 is made to a checking account that pays 3% annual interest compounded quarterly, and that's a key word right there, compounded quarterly. Okay, so if we have this amount, remember we always start with our investment in front, 270. We're going to multiply that times 1 plus or minus the rate depending on what if it's a depreciation or an appreciation. And this is going up, so this is a plus sign. We are getting 3% interest, but we are getting it quarterly. So we're not going to get the full 3 at the end of the year. We're going to get the 3% divided 4 ways. So we'll take our 3% and divide by 4. And since we are dividing it into 4 times, we're going to get 4 times as many occurrences. So when we're writing an equation for this, and x being time, whichever way you want to put it, write an equation that fits this scenario, that would be the equation that fits this scenario. Remember, the n values are going to always pop up in the denominator and then in the exponent with the variable. And then it says, how much will this be worth after 5 years? Well, in this case, all we would do is substitute in the number 5 for x. Like I said, I've already done some of these things in the calculator, so I'm just going to put the result. And the result would be $313. And since we are talking about money, we would round to the hundredths place, so this rounds up to 52 cents. Letter B, it says the value, a vehicle purchased for $12,000 will depreciate. It will decrease. So we have $12,000. And since the value is decreasing, we are going to take that amount away from 1, because the 1 stands for 100%. And it says the depreciation will decrease by a rate of 8% compounded weekly. Well, we have 52 weeks in the year, so our denominator and then our exponent is going to be 52. So we would divide by 52, and then we would put a 52 into our exponent, and then we would add our variable x or t, depending on which one you choose to use. So our equation for this scenario would be this. Now, later it asks us, when will this be below $5,000? I personally went to a table and created a table from my calculator, and 0 was 12,000. 1, after 1 year, that was $11,076.71. And I just kept going until I got below the number 5,000. And the first time that happened was actually in year 11. Year 11 says $4,974.02. So the answer, how many years until it's worth less than $5,000? That would happen 11 years later. All right, it says next, a $1,000 government bond is purchased. You will receive 2% annual interests compounded monthly. So our starting amount is going to be the $1,000. So we have $1,000. And since this is increasing in value, we will have a plus sign. It is 2% annual, so that will be the percentage that goes in the top. Compounded monthly, 12 months in a year, so that value is 12, and so is the exponent. I'm going to use a t here just to change it up. So this would be our scenario. And this one asks how much time, or excuse me, how much is it worth after 30 years? So all we need to do in this case is to take the 30 years and substitute it in for the t, the time. And when we plug that in, we get the number 1,821.21. It's actually 28.208, but the 8 rounds up to a 1. So this would be our value after 30 years. And that's a reasonable number. 2% is not a very high percentage, but 30 years is a long time. So our value is almost doubled after about 2 years. Now this one's a little bit of a tricky one. We're talking about a tree. It's currently 0.12 inches tall. It grows at an annual rate of 150% compounded continuously. Well, compounded continuously is where we're going to use our PERT formula, which is principal times the natural base to the rate times time power. But in this, we have to also pay attention at the end, because look what we're looking for. It says, how long until the tree is 3 feet tall? Emphasis on the word feet. We're actually comparing two different things here. We're comparing inches to feet. So what I like to do personally is I like to get rid of the transition right away. So what I'm going to do is convert 0.14 inches into feet. Well, since there are 12 inches in a foot, I will have to divide this by 12 to figure out how long that 0.14 inches is in feet. And what I learn is that is 0.0116 repeated. And the alternative to that is to actually put this amount in for our formula as our starting amount. So let's take a look and see what that looks like. So we're going to go to the starting amount. Well, the starting amount is the 0.14 inches, but divided amongst 12 because we're trying to figure out the feet. We can leave it that way as a starting amount as well. Since this is compounded continuously, we will use the E. Our rate in this case is higher than 100%, so it's going to be 1.5. And then on this case, we're not looking for a period of time. What we're looking for is when a value reaches 3 feet. And we've already converted it to feet, so we're good here. So I can plug this value in just like this, and then all I've got to do is look through my table and decide where this value gets higher than 3 feet. If you didn't convert it at the beginning, you will have to convert it at the end. So here's what I'm looking at. After year one for full year, we're at 0.05. Year 2, 0.23. Year 3, we finally get over a foot, 1.05. And then year 4 is at 4.7. And it does ask when it will be taller than. When it will be taller than 3 feet. So that when it will be taller than 3 feet is any year past the 4th year. We don't have a plug-in value like many of our other ones. In this one, we have to refer to a table. Good news is later we'll learn some logarithms and learn how to solve. But until then, we can go to our calculator, look through our table, and just see what we have. All right, let's take a look at these. These next two can be a little confusing, so let's see what we can put together here. So it says find the equivalent annual rate of interest 3% compounded monthly. So we talked about this before. How much are we actually getting? Yes, we're going to get 3%. That's what the annual rate is, but when we compound it, we actually get a little bit more. We actually don't have a principal amount, but we don't need one here. We will just use that formula that we have been using, which is the 1. In this case, it's plus 0.03. And we're trying to compound monthly, so we would divide this by 12. And then it would be to a 12x power. And the reason for this is whatever the amount is, it's a percentage. So the principal doesn't matter. The higher the number, the higher it'll incur, but it's still going to have the same rate. So the 0.03, we're getting 3% every year, but it's divided monthly, so we're going to only get 0.0025% each month. When you multiply that number by 12, what you'll learn is that that number 12 times will get us back to our 3%. So you're still getting 3% annually, it's just it's divided 12 ways into the 12 months. So we can convert this thing now by rewriting this as 1.0025 to the 12th power, because those are all numbers. The variable, we're kind of out of luck, to be honest with you. We can't calculate a variable because it's an unknown amount, but we can calculate those values that are numbers. And if I hit that in my calculator and I go 0.0025 to the 12th power, what I end up with is 0.0304. So you see, I'm actually getting a little bit higher than 3% interest. What I'm getting is a value of 3.04%, because what we have to do is move that decimal place over 2 times, 1, 2, and then we are sitting at our percent. It's not a whole lot, but it's free money on that case. Now the next one's a bit of a typo, I believe, because it says find the equivalent monthly rate for interest compounded 5%. If that were truly the question here, all we would have to do is take the 5% and divide by 12, because that's the equivalent monthly rate. But I think what this is talking about is finding the annual return actually if we have a monthly rate. So it's going to be just like the other one. 1 plus the 0.05 divided by 12. And this is monthly, so it would be 2A 12T. So we would have 1 plus that 0.05 divided by 2. And again, if that's truly what the question is, what we have here is that is our monthly rate. We're paying the, whoops, let me put my decimal, 0.0042 each month. So this would be 12T. And we are going to do the same as the last one. We are going to take that we're going to add the 0.0 first to the 1. So what we end up with is 1.0042. And we're going to move the 12th power down to those, because numbers will interact with other numbers, but the variable will not. And what we learn is 1.00416.2 becomes 1.051. So the decimal place, after being moved over 2 times, will put us at 105.1%. So if it's 105.1%, that means that we are getting 5.1%. Next thing we're going to look at, number 2, is we're going to start introducing our transformations. Question 2 says, f of x is the parent function of g of x. What is f of x? Well, this is a real easy one. The parent function is always going to be determined based on what the exponent is attached to. So since this is attached to a 3, it comes from the parent function, the triple family. So the parent function is going to be 3 to the x power. Nothing else matters on this. The transformations will change domains. They won't change domains, excuse me. They'll change ranges and steepness, but they will not change the parent function. So whatever it's attached to, it is. So even in like number 3, it says list the transformations. Well, we don't need to list to state this, because whatever the 2 was, it is there. But that's just there to remind you. So let's list our transformations, remembering on our transformations that the 2 does not represent a transformation. The 2 only represents the family of the functions we're in. So this is a doubling family. So let's talk about this. There is understood parentheses There's understood parentheses around the exponent. So anything happening there is horizontal. Anything else is vertical. So let's take care of the horizontal right off the bat. It is horizontal because it is in the parentheses. It is a horizontal shift because it's a plus or a minus sign. And remember, with horizontal, there are always tricks. So this feels like I should be going left 1 because of the minus sign, but we're actually going to go horizontal shift right 1 unit. Next, we'll look at the value in the back. We'll save the toughest stuff for last in this case. Well, this is outside of the parentheses, which makes it vertical. It's going to shift it up or down depending on the sign. It is a vertical shift because it is a plus sign. And we do exactly what they say. Plus seems like it would be up, and on verticals it is. It does exactly what you would think. And then the last thing is actually 2 things. It feels like that should be a vertical stretch by a factor of -3, but remember, vertical stretches can never be negative. That's a different transformation in itself. So we have a vertical stretch by a factor of 3. And we have a 4th transformation in this case, which is a vertical reflection. You could also call this a reflection across the x-axis. Both of those things are stating the same thing. Number 4, family is base 10. That has nothing to do with transformation, all to do with family. So let's start with the easy one on this case. Well, there's a subtracting directly at the back, so we have a vertical, and it is subtraction because which makes it a shift. And since it is vertical, we do exactly what it feels like, which is down 4. Next thing we'll look at, we'll take care of the horizontal transformation, which is the understood parentheses. So we have a horizontal. It is also a shift because it is a plus or minus sign. But in this case, it feels like we should be going left 3, but horizontal always have the reverse behavior. So it's actually going to go right 3. And then the last one, the 1/2 that's in front here, is vertical because it's outside of a parentheses, so we know that much. It's multiplication, which makes it a stretch. But in this case, the number is between 0 and 1, so it is a compression. So this is a vertical compression by a factor of 1/2. We won't be seeing any horizontal stretches or compressions, so you don't need to worry about those. And then number 5, we are dealing with the natural base, the E. This is going to work the same way. We've got a base of 2, a base of 10, and then now we have the natural base. So the natural base, first of all, we look to see what's being manipulated in the exponent because that's our understood parentheses. So we have a parentheses around the x plus 1, which represents a horizontal because it's inside of a parentheses, and a shift because it is a plus or minus sign. In this case, we do the inverse, so it's a horizontal shift left 1 unit. I'm also going to look for any other types of shifts that I have. In this case, a plus or minus sign, like the -3, is outside, which makes it vertical shift. And we do exactly what it says, so this one will go down 3 units. And the only thing left is the 2 that's in front. The 2 in front is outside the parentheses, which makes it vertical. It is multiplication, which makes it a stretch because that value is outside of 0 and 1. Excuse me. So we have a vertical stretch. Let me erase that. Vertical stretch by a factor of 2. The next thing we're going to look at is the visually seeing the transformations, graphing them, and identifying the domain and the range. So we are looking for the domain. Remember, the domain of any exponential function is all real numbers. So that's going to be our negative infinity to positive infinity, just like we see down there. Guys, there should be no complications here. We're not even dealing with logs yet. So if you're asked for a domain, it's from negative infinity to positive infinity. The range of all parent functions should be the same as well. The range of all parent functions, since they asymptote at the x equal to 0, y equal to 0, excuse me, which is the x-axis, since they're always asymptoting at that point, their range is always going to be y values above that, y values greater than 0. All of the parent functions you see should have that. Now the transformations are generally moved, so they can have 0, but they're usually not. So when I look at this graph, I'm going to first try to identify its asymptote, which it looks like it's asymptoting at 1. Draw a horizontal line here at 1. So we see that there is an asymptote at 1. So this thing, that comes from the shifting it up 1. So our range will be y values greater than 1. Now on all of these exponential functions, we have horizontal asymptotes. And this domain, excuse me, or this range put in interval form is from 0 to infinity, and the other one's 1 to infinity. As you can see, the answers down there at the bottom. As I was saying, though, the only asymptotes we should see on exponentials are horizontal. So in each of these, you should just go with it. It's horizontal. And the horizontal asymptote, like I drew just a moment ago, for the first parent function was y equal to 0. And the horizontal asymptote for this transformation is y equal to 1. So this function has a base of 2. So all have a domain of negative infinity to positive infinity. That's true of all exponential functions. The range is how far laterally it's going, vertically, excuse me, it's going up and down, and all parent functions have a range of y values greater than 0. We're going to write it in interval notation. So in interval notation, that is from 0 to infinity. And the range of the parent transformation function, which has been shifted up 4 units, would be all values of 4. There's our asymptote, our horizontal asymptote at 4. And you can see this graph is reaching to negative infinity. So 4 is going to be our limit, and it's going to be reaching to negative infinity. Let me correct that. Sorry, the smaller number always goes on the left in interval notation. So it would be from negative infinity to 4. We can see that written down here at the bottom. That's basically saying y is less than 4. But that's written in interval notation. The next thing we're going to look at asymptotes, and this is always going to be horizontal. So we're going to have a horizontal asymptote, and all of the parent functions have horizontal, all exponential functions have horizontal asymptotes at y equal to 0. Now, the parent and the transformation are both going to have horizontal asymptotes because that's all we can have. And since the parent function, the transformation had been shifted up 4, its horizontal asymptote will be at y equal to 4. So this function is one of the natural bases. You can see the graph over to the right. We recognize that all exponential functions have the domain of all real numbers from negative infinity to positive infinity. And we'll look at the range as well, remembering that the parent function is always going to have the range of y values greater than 0. So that's from 0 to infinity. And since our transformation has been shifted down 3 units, as we can clearly see, the range is from negative infinity to, or negative 3 to positive infinity. Both have horizontal asymptotes, as all exponentials do. The parent function has the horizontal asymptote at y values equal to 0. And since the horizontal asymptote was shifted down 3, it has a horizontal asymptote at y equal to 3. So now we'll move to solving these exponential functions. First off, whenever we have an exponential function that have the same base as these first ones do, all we have to do is cancel those bases and set the exponents equal to one another. So this one would be x plus 1 equal to 5. Subtract the 1 from both sides and our x equals 4. I'm going to move to letter C here. Letter C, we don't have a common base, but we can get a common base. What we need to do is generally look at the base of the smaller number, which in this case is 3. It's 3 to 2x power. And we're going to work through the powers of 3. 3 to the 1 power is 3. 3 to the 2 power is 9. 3 times 3 is 9. Times 3 is 27, which is the number we're looking for. So 7 is 3 to the 3rd power. I also showed you with your calculator some time ago where you could go to your y equals and type in the xth root of whatever number you're interested in, and then look through the table until you see integers. But we now can tell, though, that 27 is 3 to the 3rd power, so we're going to replace 27 with 3 to the 3rd power. Now that we have that common base, we can cross out the common base and set the exponents equal to one another. So 2x equals 3. We would divide both sides by 2, and x would equal 3/2. Now we'll move to letter B. We also recognize that these do not have a common base. Let me again encourage you, do not divide. Do not divide. A lot of times we see numbers like, oh, they got a common factor. Well, a lot of times they have a common factor because they're both from the same root. But we cannot divide by 2 here. What we need to do is find a common base of 4 with 2. So basically, 2 to what power is 4, which that one we can do mental math tells us 2 squared is equal to 4. So since 2 squared is equal to 4, we can replace the 4 with its equivalent, 2 squared. So what we end up with is 2 to the 4x power equals 2 squared to the 3rd power. Now this brings us to an exponential rule, and the exponential rule tells us a power to a power. Well, what do we do? Well, if you ever forget these things, usually it's pretty obvious. It's either adding or multiplying. So if you're not sure, put in your calculator and see what works. But what it is a power to a power, you should be multiplying. So 2 times 3 is 6. And again, put it in your calculator and see if it comes out to 2 to the 5th or 2 to the 6th. Should be an equivalent amount. Common bases will cancel. Common base of 2, so we mark those out. And what we're left with is 4x equal to 6. We would divide both sides by 4, which is 6/4, but it reduces to 3/2, which is actually the same answer as letter C. Now, I did a graph for you here, and I'm going to show you how sometimes the graph on these can be more confusing than helpful. I can't tell at all if those are graphing towards the left as they're asymptoting. It looks kind of like as we move right, the green line and the blue line may be approaching one another, which makes me think, well, maybe they're going to cross one another. It doesn't look as if they're parallel, but we'd have to see. And they're not asymptoting, so if they are approaching each other, they will actually touch. But the graphing calculator actually is a mess here. I tried zooming in and out trying to find it, and it was just way off. So sometimes the calculator is not even the easiest way. What we're going to do is do this algebraically. And 9 is 3 squared. That would give us the common base of 3. Remember, do not divide. Do not divide by 3. So with the common base of 3, we can cross those out, and we're left with x plus 4. And I'm going to go ahead and distribute the 2x, the 2 to the x minus 1, and that is 2x minus 2. We subtract the x from both sides, and we add the 2 to the other side. So now that I know that the answer is 6, or think the answer is 6, my search is a lot smaller whenever I go to that graph. So I'm going to pull up that graph again, but with a different view. Now that I know it's on 6, you see 6 is not even on the screen here. But now that I know the answer is 6, maybe I can adjust my windows to make this work. And I actually worked really hard to get this one because those numbers are actually counting by, I believe, 10,000. So my windows are very funny, but I can clearly see that they are crossing at 6. And like I said, I believe those are counting by 10,000s, if not more. And then the last thing is using your calculator to solve these. I'm going to show you 2 ways, and then the last 2, I'm just going to pop the equations up there, and you can decide what you want to do on these. The way I prefer to do these is to move everything to one side. So what I want to do is move the 2,000 to the other side to join everything else, and then we're set equal to 0. And what happens is we have these set equal to 0. So now we can graph these and see where they cross the x-axis. I personally like to just look for x-axis interaction. So we go minus 2,000. This equals 0. Anywhere that it crosses the x-axis is the solution. And then it can only cross once, by the way. So I'm going to pull up this graph. It's going to be a little small, I imagine, so I'll write this answer over to the side for you so you can interpret it a little better. You can see the equation. You can see the answer of 13.721. That's where I put in the equation. There's my answer. So x is, and this is an approximation because we did do some rounding here. So this is approximately, my equal sign is squiggly there, 13.721. Now, the next way we can do this is to graph them both and see where they cross each other. So there's the 20,000 times 0.88 to the 12t power. And then there's 10,000. So what I can do is I can graph each of these independently and then see where they cross one another. This one's going to be my y1, the 20,000 will be my y2. When I graph these things, I'm just going to look for an intersection of the 2 lines. So you can see my blue line is my 10,000 line and my green line is my equation. And I can see that those 2 lines are crossing at 0.452 So that is the solution to this equation. X at a value approximately 0.452. And the last two, I'm just going to pop the equations up here and show you the result. See, I moved the 15 to the other side for this one, graphed it, saw that it crossed at 50.373. So my X is approximately, not equal, is approximately 50.373. And on D, again, there's the graph. See it move the 10,000 over. I see that it crossed at 27.304. So that is my solution. So you can graph them independently, see where they cross, or you can put everything on one side, graph, and see where it crosses the x-axis. That one is always my preference.